Hey Chico, how is it going? Okay, I mean, not much feedback yet. Are you ready?
We're rolling.
Oh, we are? I don't see anything on the screen here. Okay. Now we're rendering this is really the third part of our class. From now on we're going to take some a little bit more theory today, but this is going to be a theory related to applications. So I won't make you try to solve quantitative problems on that theory, at least not much. Now the homework that you have on the web page right now is actually a revision of questions from the lecture notes. So it is going to make you go back and read the lecture, but you don't have to really do a complex homework, or you don't have to write much in terms of a solution to that homework. I mean, you just write one line of text or a formula and move on.
Is that the one due Thursday? Or is that the one due next?
This is the one that's due next week. You still have this is the homework for this lecture.
Earlier in the afternoon.
I just posted it maybe half an hour ago. So you see it, it's not a complex homework, it's just solutions from the lecture. And this lecture is related very much to the practice of colloidal science. Whatever you do, whatever types of particles or colloidal systems you use, you need to characterize it sooner or later. And the most powerful tool for characterization is scattering. And you can do light, which is the usual case. You can also do X-ray, and one very powerful technique is neutron scattering. So what we want to do in this lecture is really understand the basics, which are quite complex. So I have tried to really give you the general picture, and then learn a little bit about the practical aspects of using different types of scattering techniques in colloidal systems. Now what you see here is a small movie, which is made by my collaborator, postdoc Simon Lumsden. What you see is you see a pattern here, which right now is diffuse. At some point, this diffuse pattern suddenly starts morphing into these 6 spots. Now, how have we collected this pattern? We have a small cell with a colloidal suspension here, on top of the movie. We have a laser, the beam of which goes through. You can actually see the beam of the laser hitting here, right in the middle. However, when the laser goes through the colloidal system, if the system is organized, we see this pattern of 6 spots, which gets turned on and off. The on and off turning of this pattern is because we have the particles in the suspension being organized by the electrical field, and then being disorganized when the field is turned off. Now guess which is the organized state?
The dots.
Right. The dots show that you have some specific, which is throughout the sample, you have some specific long-range organization which is reflected into this very well organized scattering pattern. If you don't have organization, as you can see, instead of a dots, you have a diffuse bright ring. Now, what we're going to study in this lecture is actually why do we have this type of scattering, how do these rings occur, and what information they can give you about different types of colloidal systems. So let's move on. This movie can repeat itself forever. Now the general scattering system, that a generic scattering system, is like that. You have a suspension, you have particles, micelles, molecules, biomolecules, whatever, in the suspension, but it is inhomogeneous system inside. You shine a beam of light, X-ray, or neutrons. Of course, most of the beam would continue. You don't want that typically. You cut it off. But then you can measure the intensity of the scattered light at different angles using a detector. Now, there are 2 very general modes of scattering. Now, the first one is the typical scattering technique where you just shine the laser beam or whatever beam go through the sample, and then you check out the intensity at some angle and at some angular orientation. Now this is time averaged. Obviously you don't resolve what happens exactly, you just measure it, the average intensity. Now this is called static scattering. which is the one of the usual modes scattering, and it gives information about the colloidal size, shape, and interactions in the system. There is another mode of scattering which we're not going to discuss in too much detail, but I'm going to give you the most important things, which is called dynamic scattering, time-dependent scattering. In this case, let's say you have a detector here, and your detector measures the intensity of the light very fast, kind of on a nanosecond level, and measures the fluctuations of the intensity. And it is also a very powerful technique which can give you some fast information about the dynamic kinetic properties of the system. And from there on, you can resolve some of the size characteristics of the particles. So this is what we're going to discuss today. Most of the time we'll go on with static scattering. So let's do some physics here. Just a definition of the system. You have particles. The size of each particle is 2 times its radius, which in this case is going to be defined as 2 times large r. Supposing that you can define something like an average or typical distance between the particles, we're just going to use the running coordinate r, and you're going to denote the distance from one particle to the other one as r, or r can just be the radial coordinate from the center of the particle. Of course, you know what wavelength of the light is. You can imagine what the scattering angle is. Excuse me. This is the angle between the direction of the falling beam and the direction of the beam which is scattered, diffracted at a certain direction, which we're measuring. So our detector would be here. Now, physically, people don't like to use scattering angles. Rather, they prefer to use scattering vectors. And you can see that actually the scattering vector is a simple relation between the wavelength, a few constants, 4 times pi, and the scattering angle divided by 2. Now, why do you prefer to use the scattering vector rather than the scattering angle? You can see that the scattering vector actually is invariant of the wavelength and the scattering angle. You can have, if you change the wavelength, the scattering angle is going to change too, but the combination of both is going to remain the same, in the sense that this kind of like eliminates the wavelength as a factor in your measurements. This means that if you have a certain scattering, if you just change the wavelength, you are going to have the same scattering at another angle. So the scattering vector is the physical invariant which people prefer to use in these calculations. And now this is the very basic and most important formula for scattering, which you have to take off. I'm going to explain it physically a little bit, but for now you have to take it as granted. The intensity which you're going to detect by your detector at a certain scattering vector, which means at a certain wavelength and a certain angle, is going to be a function of the optical density of the particles. This is how much the particles scatter. Let's say the difference in the refractive index times the number of particles. This is a constant which just tells you that different particles scatter with different intensities. Then you have this function here, p, a function of the radius of the particles and the scattering vector, which is called the particle form factor, and which tells you how the scattering intensity is going to depend on the form, shape, and size of the particle. And then you're going to have this function, which is the so-called structure factor, which tells you how the scattering intensity is going to depend on the structure of the particles in the system, the average distance between the particles, the eventual organization of the particles, and so on. This function would be a function of the radial coordinate and again the scattering vector. Now physically, why do you have these two functions? Eventually all scattering that you see is eventually diffraction. This means that, let's say, your light wave is hitting this particle, and you have, let's say, these two beams, one hitting on one side of the particle and the other one hitting on the other side. These two waves are going to interact with each other, and this is going to determine the intensity which you're going to register between these two waves here at a certain angle. The interaction, the intensity is going to depend on the angle. However, you can have diffraction and interaction between the beams from this particle and that particle. Now, the distance between these two waves, interacting waves, diffracting waves, is going to be comparable to the particle radius, right? The distance between these two diffracting waves is going to be comparable to the distance between the particles. So if you want to kind of account all the diffractions in the systems, you have to account for the diffraction from each particle, and then you have to account for the diffraction between particles, kind of interparticle and intraparticle diffraction. And those of you who happen to be kind of, let's say, would love physics and mathematics, can actually do complex calculations and find expressions for those functions. What I'm going to do is I'm going to give you some simple expressions just to illustrate the basics of how you do those calculations and what types of expressions you get. Let me go one slide further and I'll stop for questions. Now, how do you obtain any type of scattering function? Kind of what is the relation between, let's say, the shape and form of the scattering body and the shape and the form of the scattering pattern? Let's say you have some particle here, and then you have some specific scattering pattern, like the ones that I showed on the screen. Now, what is mathematically the relation between this function here, which is the scattering density, and this function here, which is the scattered intensity? Mathematically, the relation between these two functions is, like it's a vectorial relations, which gives you this thing here, which is essentially the difference between the scattering from the particle and the scattering from the media. Kind of how much the particle stands out from the media. The more it stands out, the more it scatters. So this is essentially gives you, kind of includes the shape of the particle, or the shape of anything scattering, any scattering pattern. And then you have this function here, both of which give us what? This is a general Fourier transform of the function of the scattering object. Now, the scattering object in this case may not be a single particle. It may be, let's say, you have many particles, and you have a function which describes all those particles together. So if you know how these particles look, by making a Fourier transform of the particle shape, you're going to get eventually the outline of the scattered intensity. So the Fourier transform of what you have in this screen, which is the diffraction screen, is going to be the diffraction pattern. Now, for systems which are homogeneous, usually isotropic, you can actually replace the general Fourier transform with the sine Fourier transform. So you can use only the sine part of the Fourier transform. So you have a much similar integral to solve here for the relation between the shape of the scattering object, or the scattering pattern, and the actual scattered pattern that you're going to see. So this is the formula which you're going to use right now in order to derive different expressions for the form factor and the structure factor. Okay, yeah, time for questions.
Can you explain again when you can use this simplification?
This is for the case of, now first of all you have to have static scattering, which means that this is the time average function. Second of all, typically you have to have isotropic particles, which means that the polarization of the light should not change when it hits the particle. So if you have a vertically polarized light, it should remain vertically polarized when it goes to the particle. Otherwise, you have to use the complex function because the angle of the light is going to change, and that's where those eyes come in and so on. If you just have a very simple scattering, you have particle which has, let's say, different refractive index. The light hits it, the particle does not move. The light hits it, it does not change its polarized angle. It goes through and scatters. This is the case where we can use the sine Fourier transform. Nobody uses the other function actually, at least nobody from people who do not specifically do some type of scattering research. And I'm going to give you simplified expressions for the sine functions right away. But I want you to understand this basic kind of like correlation between the scattering intensity, diffraction, and so on. Any other questions here? Again, whatever you do, I'd like you to think about what is the form factor, what is the structure factor. And there would be usually some parameter in front. Typically, let's say difference in the refractive indexes, which just gives you the actual scattered intensity. Okay, then I assume so far so good. Yes, Helene?
In the formula for the scattering vector, like where q is equal to 4 pi by lambda,
Right.
there should be a limit, like a range for that, because sine can only vary between like 1 and minus 1. So we cannot change the lambda indefinitely.
Right, but I mean, like if you think about scattering, imagine that this is your scattering plane, this is your scattering angle. The highest scattering angle that you can have is backwards, right? So it would be theta would be like from 0 to 2 times pi. And it's pi over 2, so it's going to be like, I mean, essentially you're going to have sine from here to here. Scattering from, so essentially it tells you that kind of cube changes from straight down to essentially coplanar with the scattering plane. So this is the natural limit.
Yeah, but lambda can't be changed. It can only be changed in a particular limit. Like if we keep on
Right.
increasing the lambda.
So you have kind of, if you think in more general terms, this is a very important point. There is a general correlation between lambda and q. I mean, there are values for lambda for which you can have a physically reasonable q.
Yeah, that's right.
And this is very important. This is actually why we have to do light, X-ray, and neutron scattering. Why can't we just use light and do both scattering by light?
Can't see anything below
Right.
100 nanometers.
I mean, you see it emerges from the formula, but you can only have, I mean, as much scattering from a certain system, which is dependent on the size of the system and the wavelength. So you see this appearing right now on the next slide. So let's start with something simple now. We have, imagine that we have very diluted particles, so we don't have any interaction between the particles. Kind of, they don't diffract between themselves. All the diffraction that we get is from the particles. This means that the scattering function is going to be what? Yes, Shishin? 1, right. I mean, if we don't have scattering between the particles, the scattering function is 1, not 0, right? If it's 0, we won't have any scattering at all. So scattering, the scattering factor is equal to 1. Now what is the form factor? So all scattering that we get is from the particles themselves.
The scattering factor, you mean the structure factor?
Right, the structure factor. Yeah, sorry. S of q is equal to 1. P of q, which is the form factor, should depend only on the particle shape. So in this case, we can immediately write the radial integral here, assuming that we have radial symmetry. Of course, we're going to derive the formula for spheres. So we assume that we have radial symmetry. We solve in this integral for spheres, assuming that this is constant, equal to delta B. So we have anisotropic sphere. The refractive index is the same all over through the sphere. This goes out, the remaining integral from the boundaries of 0 to r, when integrated, is going to give us this solution. This is the scattering essentially the scattering function from spherical particles. This tells you how spherical particles are going to scatter light in the radial direction. You have all, as you can see here, all of those formulas are dependent on Q times R. So we're going to investigate how Q times R actually relates to the scattering pattern. If you solve this mathematically, you're going to find out that this is a decaying function which has certain minima at certain distances, which is periodic. So it's a periodically decaying function. If you do an experiment from a particle which is comparable to the wavelength of light, you're going to find out, I mean this is really almost a real experimental image, that you're going to have such a scattering pattern. This is the same pattern in terms of intensity. So essentially you're going to have some rings around the particle, scattered from the particle. You have seen this in real life even, but I won't discuss this right now.
Where did that square root come from?
The square root comes from because just the way the dimensions go and so on, you really have to take the square root of that. Now, if you integrate that, you're going to find the electrical field intensity. Now, in order to get the intensity, you have to square the electrical field. So that's why it this one is kind of essentially this one squared is going to give you the intensity. Without squaring, it just gives you the field. Okay, and now again, let me remind you what I have just copied the same formula here. Now there are different regimes. You can say how large is the wavelength compared to the size of the particle. And these are the different types of. Now, if you open a book, you're going to find some very complex kind of like thumb rule calculations, which leads you in thousands of constants, and then end up with different types of scattering. I have really tried to give you the top-down view here. But the miscattering is when the particle size is comparable or larger than the wavelength. This is the case where Q times R is going to be on the order of 1, or the radius of the particle compared to the wavelength should be about 1 to 10 or so, which means that the particle should be relatively large, micron-sized particles, for example. Or you should have small wavelength. So that's why, for example, when you use X-ray, you can obtain this is a comparison between the theoretical scattered intensity and the scattered intensity, the fitted scattered intensity, which people have obtained from scattering from a relatively spherical protein molecule from X-rays.
Yeah. If you read the caption, I think they actually...
It says solution X-ray scattering of some bacteriophage compared to the scattering calculated from a uniform sphere of radius 133
But
angstroms.
look what it says. It says solid curve, bacteria, dashed curve, theory. And that, I think that's
Well, that's wrong. I mean, the dash curve should be experiment. I mean, like the experiment, what happens here is you can see that this is a logarithmic scale.
It gets smudged too.
The theoretical, I mean, it's very easy to theoretically calculate more intensities. But experimentally, you are like eventually going to the level of noise. So you can't go below that level. So that's why you register only 1, 2, or 3 rings. And you can't register like 10 rings just because this function is decaying. So it decays very fast when you go to higher Qs. So this means that eventually you can take suspension of particles. If you have this type of scattering, you can very, very well fit their radius and find their shape. There are formulas for all types of particles which have been developed theoretically. Ellipsoidal, needle-like, and so on. What type of scattering function you're going to get. You can take the scattering pattern, you can fit it, and you can obtain the particle size. This is also routinely done for emulsions. To measure emulsion size, for example, because emulsion particles are micrometer in size and they are exactly in this scattering regime.
Is this graph is then an example of the my scattering?
Right. My type of scattering. Niche. Huh?
Yeah, okay.
Actually, it's me.
Me.
Right.
Didn't you just say that they had to be micron size and then?
Right, but this is X-ray scattering.
Oh.
If you use wavelength of light, which is sub-micrometer, the particles have to be micrometer. If you use X-ray, which is angstrom, tens of angstroms, then you can go to tens of angstrom size of particles. And that is the reason, again, why it also relates to the question of Shalini here. This is the reason why we can't, and we can discuss this immediately right now. Well, that's what I have written here there, particle size much bigger than wavelength. This is the reason why, if you want to find out this me type of scattering, if you want to find out the particle form factor, the wavelength of light should be comparable to the particle size. If you want to measure something small, you can't do this with light. You have to do this with X-rays or neutrons. So for protein, you use X-rays.
So the expression R over lambda equals 1 over 10?
It's, I mean, this is an approximation. I mean, like just this is the calculation for on the order of 1. This formula would work for, let's say, 10 times more or larger particles.
Okay.
But if you have, now what happens if you have very large particles?
No scatter.
Yeah, I mean the scattering, because you have this term here, I mean the scattering is going to be so small. So that's why you don't see scattering from this object, right? I mean you see it, but you don't see it like this. If you take a microscope and zoom in on the edge of the object, you're going to see actually one diffraction line. But that's the reason why when you see objects around cars and so on, you don't see them like rings around them. Although if you take a walk, now you have seen something, if you take a walk through, when you drive through fog, you have noticed that actually sometimes you can see rings or you can see kind of halos around bright objects.
Headlights.
This is actually scattering from the form factor of the fog. The fog is a relatively sub-micrometer type of droplets. And when you have these droplets in air, you can see actually the halos, which is scattering from the fog. But if you can take an object like that and you don't see the diffraction pattern here. You're going to see diffraction pattern if you use what?
Radio wave.
Right. I mean, that's why for radio waves, I mean, you can actually see lots of diffraction phenomena. If you listen to FM and if you drive around, you can have some very sharp places where you have suddenly very sharp deterioration of the signal. This is just because when you drive around, I mean, you just drive past a metallic object or something like that, and you go through a diffraction minimum where it scatters. You've probably noticed this, like when you go drive around. I mean, just to stop at some place, and it's very narrow band, but you can deteriorate the sound. Okay, now let's discuss the other cases. Now, what happens? Again, this is the same formula. Now, what happens? This is the general integral formula. What happens when Q times R approaches 0? So you have very small particles compared to the wavelength. Now, you can have two approximations. Now, if you just say it really approaches 0, then this term here approaches, the limits of this term approaches 1. So when you integrate what is left here in this integral, you just obtain the volume of the particle. Or if you speak about molecules, you obtain the molecular weight. This formula tells you that the particle, the small particle, is going to just scatter depending on its volume. The larger the volume, the more it scatters. But you're not going to have any angular dependence or any significant angular dependence. The scattering pattern, even when you're not too close in this region, is more or less you don't see any diffraction rings. This is actually, if the light comes from here, that's how it's going to scatter uniformly. If it's even smaller, it's going to scatter exactly radially in every direction. Now, there is some interesting question here. Let's discuss it later. Now, one expression which you're going to use, I have given you just the basics, the result here. You can do the calculations if you like. What happens? Now, this is already squared, so you can see the square here. So that's why you don't have the square root here. What happens if you don't assume that it's exactly 0, but you just take the first term in the Taylor series? When you solve the equation, you are going to obtain that the form factor is going to be proportional to 1, kind of the volume, minus this term here. And Rg here is not the radius of the particle, it's the radius of gyration of the particle, which for spherical particles is 3/5 of the squared radius. Of course, this is the squared radius of gyration. Now, why do people use radius of gyration? Because this very formula is very useful for polymers in solution. And the parameter which you use for polymers in solution is the radius of gyration. We're going to use this expression in a few minutes from now. But right now we just derived it here, kind of, I mean, this is a limiting, but not so strongly limiting case as this one. So let's summarize here. If the particle is very small, the scattering is just proportional to its volume or molecular weight. Of course, whether you use volume or molecular weight, I mean, you're going to have different dimensionality for this factor here, which tells you the scattering intensity. Because physically you have to obtain the same dimension. If the particle is not that small, you are going to have this form factor, which is 1 minus the scattering factor times the radius of gyration squared over 3. We're going to use this in a second. Now, one kind of, okay, let's see fastest thinking question. Now, if you think about that, kind of the simplest thing that scatters is, I mean, any molecule is a particle itself, right? And we have molecules all around us. And according to this formula, it may be small, but it still scatters radially in every direction. Now, why then the light goes through the air and it doesn't get scattered around and disappear?
Because there's no structure to there.
Right, that would be a good answer. You have many molecules, they scatter uniformly, there is no structure. So essentially all light except the one which goes straight through just cancels itself out when you average over all molecules that scatter. If you have only one metallic particle which scatters a lot, and you put it in the beam, you're going to see it fairly well. It scatters. If you, however, put lots of metallic particles, they're going to, actually metallic particles are going to absorb light, but the point is that dense media don't scatter just because the molecules are close and they don't have some specific structure which allows them to scatter in any direction but forward. Kind of self-canceling out effect. Let me delete this one. Okay. Any questions so far? Now this was the easy part. Okay. Now, so far we calculated knowing the shape of the particle. Now, the thing that we have to calculate next is how is the scattering going to depend on the difference between the particles in suspension. Then the question is, can you define some parameter which gives you, let's say, the average distance or the preferred distance between particles in suspension? Is there any parameters like that? Now, people who have taken statistical thermodynamics class recently should tell me what this parameter is.
Radial distribution function.
Right. I mean, for the sake of everyone, let's just kind of go briefly through that. The radial distribution function gives you the number of particles which you're going to find out if you, let's say you have a dense system. You select the center particle and you start going around in thin spherical shells. The number of particles which you're going to find inside the shell at a certain distance is essentially the radial distribution function. What you have here is when you go further out, this is for example for a crystal. When you reach the first 6 neighbors, you're going to find 12 actually for a 3-dimensional crystal. You're going to find 12 particles in the first shelf around the particle. When you move a little bit further out, you're going to find some more particles. So when you move a little bit further out, more and more. If you have a crystal which starts to melt, you are likely to find these particles around there, but they're going already to be out of exact alignment to the crystalline lattice. So you don't know whether your particle is going to be exactly where it was supposed to be, or it's going to be a little bit further in or out. And eventually, if you have liquid, and we already have seen this function, if you remember what happens to a liquid to a wall, the same thing happens to a liquid around the particle. There is a high probability that there is going to be another particle close to it. There is a relatively small probability that there will be another particle, let's say here, which would be about 2 times the distance from this particle to that particle. But this particle may be here, or it may be, let's say, here, and it's going to be out of place. So the probability is kind of oscillatory, but it decreases. And in some cases, depending on the types of interaction, you can have actually repelled zones, attracted zone, and so on. So eventually the relation between the radial distribution function and the interactions between the particle, this is a very basic, I think we mentioned it someplace, very basic relation between the energy of interaction and the radial distribution function. So essentially the likeliness of having another particle here is dependent on whether you have positive or negative energy of interaction between these two particles. Kind of if the particles like each other, they're going to stick to each other, and you're very likely to find another particle exactly 1 particle diameter away from the surface of the first particle. If the particles repel each other, you're not likely to find another particle close because they're going to be far away. Now, why do we need this radial distribution function? Because this is the function which tells you how far the other particle is relatively to any other particle in solution. And this is the function that we're going to integrate in order to obtain the scattering factor. Yes?
Does that function take many body effects into account or not?
Yeah, I mean that's essentially the function which takes many body effects into account. Well, I mean, it depends on how you calculate it. Now, this is the simplest expression, which just takes pairwise interaction.
Yeah.
Now, if you want to calculate it explicitly, there are complex relations, Onsager relations, and so on, which may take into account the many body interactions.
So that you take into account by changing the W of R.
Right, but then, I mean, like it becomes a complex, integral, differential set of equations, actually. I mean, there are simplifications, and you can do some calculations about that. But, I mean, essentially, you usually end up with, let's say, 3 body interactions. And this is where the math kind of, I mean, like really leaves you dry, because, I mean, it becomes too complex after. The simplest relation, I'm just kind of trying to explain the basics here. The simplest relations is 2 body interactions and radial distribution function. If the particles attract each other, then they're going to be likely to be close to each other. If they don't attract each other, they're likely to be far apart from each other. And this distance is actually the one that's going to go into the diffraction pattern, because we have to know how far they are in order to know how intensely they diffract at a certain angle by taking the Fourier transform of the function. So all calculations from now on assume that we know, or you can measure, or you can calculate, as we know in this class, the pair interaction function. Or you can use, and this gives you the power of the method, you can use the scattering to determine the pair interaction function and then determine the interactions, the radial distribution function, and then determine the interactions. So that's what the power of scattering is. I mean, it relates the diffraction pattern to the interactions ultimately. So that's why when you measure the form factor, you get information about the particle itself. When you measure the scattering factor, you obtain information about the interactions in the system. So let's go through this mathematically, and then we'll have time to discuss questions again and so on. Now, the radial distribution function has to be normalized with respect to 1. Because if you don't have any kind of interaction, I mean, you're going to have uniform distribution. You're not going to have 0 distribution. So essentially, the distance between the radial distribution function and 1 is the one which gives you whether we're likely to find particle or not at some distance apart. Sine Fourier transform of that, 4 times pi, the scattering function here, dr, we have 1 here, again, like, that's how the scattering factor is constructed. Now, don't ask me about all details here and why we don't have this square root here. I mean, just the calculation and construction of the scattering factor leads to this integral. We know that this is the Fourier integral. Now, the other one is normalization factors and so on. So, you eventually end up with this scattering factor. Now, this is not an easy function to calculate, especially knowing that this function is an exponent. So exponent of another complex function, which is the interaction function, minus 1 times this sines and q's and times and so on, is really not an integral, easy integral to solve. But then, of course, assuming that we have small particles, which is very often the case, so this term here goes to its limit of 1. We can immediately derive some simple, useful expressions. And we're actually not going to solve the integral here because we don't need to. We're going to relate it to physically measurable parameters. Now, if this drops out as 1, then what we're going to have in the integral is going to be 1 plus the density of the particles, the scattering density, 4 times pi, the integral from 0 to infinity of the exponent of minus the interaction potential, minus 1 r squared dr. Now, we have already seen this formula. If you remember, when we discussed biomolecules, this is the formula for the second virial coefficient, which gives you the non-ideal, the first non-ideal term in the osmotic pressure of a suspension of particles or molecules. So then we can replace here 1 minus scattering density times the second virial density of the particles times the 2 times the second virial coefficient. Now, remembering that the second virial coefficient is actually, this is the expression for the how the osmotic pressure relates to the second virial coefficient. You can check out that eventually if you take the inverse derivative of the osmotic pressure to the concentration times kT, you are going to eventually obtain this expression here. So then we can say, and now this is a scattering again, like I have put in 0, just to remind you, this is scattering at low q's. Small particle or small scattering angle. So the scattering function at low q's is going to be equal to kT times the differential of the concentration with respect to the osmotic pressure. And we know what this differential is. So what we could do right away is we can say, okay, S, the scattering factor, is equal to kT times the differential of this one, which is going to be equal to this expression, 1 over the molecular weight plus 2 times the second virial coefficient times the this Cp, like, I mean, I've just left it because I copied the formulas, the concentration of particles. So the scattering factor at small q times r is equal to 1 over the molecular weight plus 2 times the virial coefficients times the concentration of the particles. Any questions so far? We've almost gone through the hard part.
Should it be 2 or 4?
I think actually I shouldn't have put 2 here. Sorry.
Okay.
I think that's my
what I
mistake.
thought, yeah.
This 2 here is in excess.
Good memory.
Like writing all those formulas in one afternoon is. So the 2 comes here. The 2 here comes actually from the differentiation of the concentration with respect to C.
Isn't the same thing as CP?
Now this is a tricky question, and let me tell what the answer is. Now A here should include the concentration times the scattering density. Now, which means that N is kind of like related to Cp, but you also have to have an additional constant which takes into account the scattering density in order to be able to convert from concentration to light intensity. So physically, both are concentrations. They don't have the same dimension though. Now, we don't care really too much about that, because I'm going to give you, I just want you to get a feel of how this formula derives. I mean, we don't want to concentrate on all small constants here. I'm going to give you the right formula right now, where all the constants have been accounted for, and it makes a terrible kind of like cluster of constants, as you're going to see. Terrible also experimentally, because you have to measure them. So, kind of, I'm going to give you what I want you to concentrate here is like, I mean, where do this come from? What is this term, and how does it come here, and so on? The constants which relate actually the scattering factor to the actual intensity, which carry dimensionality, are kind of, I mean, neglected here. This is what you're going to find in the textbooks, but it doesn't really help you understand what happens. Okay. So right now we're happy because we have a formula which relates the scattering factor, molecular weight, and second virial coefficient, and concentration. We also have a formula, oops, the other way. We have a formula which relates the form factor in this same case, which would be equal to the molecular weight or times the volume of the particle times the scattering factor. This is the one that we're going to use. So then we can say like that. Now we have the scattering factor for the limiting case. We have the form factor. We can plug them together in the same formula. And we can construct a formula which relates intensity to form factor and scattering factor. Now the form factor, actually, we're going to use this expression for the form factor. And in the first derivation of the formula, which is the most important practically used one, we are going to assume that the form factor is simply 1. We are going to forget about this term for now. We just derived an expression for the scattering factor. The intensity, which you measure in a light scattering experiment or any type of scattering experiment, typically it is given by the so-called Raleigh ratio. This is the experimentally measured intensity, dimensional. And this Raleigh ratio is going to be equal to the protein concentration of the particles times this constant here, which adjusts any dimensions, which includes any optical parameters for scattering, times the structure factor, times the scattering factor. We plug in this, we have concentration of the particles, optical constant, 1 over molecular weight plus 2 times the second virial coefficient, the concentration of the particles. This is minus to the minus first power. Now, for the sake of all people who would like to know exactly what the constant is, here is the constant. 2 times pi squared, refractive index of the particle squared, the difference in refractive, okay, this refractive index actually of the system squared, effective refractive index. The difference between the refractive index of the system, the differential between the refractive index of the system and the concentration of the particles, squared, Avogadro number, and wavelength to the 4th power. The problematic function constant here, which is difficult to find when you make such measurements, would be what?
E and DC.
Well, K, I mean like in K, to calculate the K, what is the problematic constant here? Yeah, Rach was right over there. Which is the problematic constant out of those set of constants, the problematic number?
Yes,
If you do real light scattering, you have to find this numerically.
Was that because finding the derivative is difficult?
Yeah.
Was it that because
Right.
there's noise in the measurements? Or?
Well, it's kind of, I mean, to find the derivative, you need to make a measurements of the refractive index with very high precision in a high range of in a range of concentration, and then you have to fit it with some curve, and then you get the derivative. And because now you're having here the Woods system of particles. Let's say you add polystyrene particles to water. Now you have 1% of polystyrene particles. This is going to increase the refractive index of photo with approximately, let's say, 0.1%. Now, what happens if you have 2% of latex particles? It's going to increase it with an additional 0.2%. So the NDC is going to be on the order of 0.1% of n, which makes the measurement tricky. You either find this in a textbook, or you go and find some very, very precise refractometer, especially if your particles don't scatter that well. When they don't scatter that well, the NDC is small. The NDC is essentially how much the particles increase the refractive index when you add them in the system, the overall refractive index. So this is the problematic constant usually. Luckily for some polymers you can find it in the textbooks. Not that luckily, when you find it in the textbooks, it may be measured at different wavelength, and it's dependent on the wavelength. So if you're really lucky, you're going to find the constant DNDC in the textbook for exactly the wavelength and the concentration range that you have in your system.
And the same solvent also.
Right?
And the same solvent.
Right. I mean, so if you don't work with water, I mean, like Raj knows these things because he works with polymers, and this is the major method for characterizing polymers in suspension or solution. So you have to have the same polymer in the same solvent at the same wavelength, the same temperature, and the same concentration range. And you can find some data in the literature, but sometimes you have to measure it, and it's no fun. But right now, once you know this constant, then you can write this expression in this way. The optical constant times the concentration divided by the intensity is equal to 1 over the molecular weight times 2 plus 2 times the second virial coefficient times the concentration. This function, if you take this as the variable, this is the function and this is the variable, you have a linear relation between the function and the variable. So this is the basic expression for static light scattering. This is what you need in order to do light scattering. This is the practical formula. And I'll discuss how you measure it experimentally right now. So what you do, you take your system, you prepare solutions or suspensions in different concentrations, find out the value of this constant if you're lucky to find it, or measure it if you can measure it precisely. Then start measuring the scattering intensity at different concentrations and then plotting it in this scale, K times the concentration divided by the intensity as a function of the concentration. What you're going to do is you're going to get set of points, and when you interpolate and extrapolate, you are going to find out the second virial coefficient from the slope, and you are going to find the inverse of the molecular weight at the intercept. One of the things which kind of like outlined my postdoctoral research was measuring the second virial coefficients of protein solutions, which is an extremely difficult task, and I find kind of like pride myself in being one of the first people to obtain reliable data there. This is what happens with the same protein, lysozyme. when you do light scattering at different conditions. If you have low pH, far from the isoelectric point, and low ionic concentration, what do you have?
Charge.
You have charge, you have repulsion, which means that the virial coefficient is going to be positive. The proteins don't want to stick together. If you have protein at high pH, close to the isoelectric point, and high electrolyte, you can see that the slope of this line changes from positive to negative. So the protein interactions move from being attractive, from being repulsive to being attractive. And what you can see here, luckily, with the exception of this very extreme case, where the proteins may denature a little bit, all those curves intercept here at the same value. This value is within 10% or less than the molecular weight of the protein. And if these curves didn't kind of like, I mean, this is a Fritz without, this is just two parameter fits. So it's not that I have adjusted this point. I was lucky that they crossed there. If they haven't crossed here, I would be in deep trouble because this is, and if this value was not comparable to the molecular weight of the protein, I would be in deep trouble because this means that my data is not going to be reliable. Luckily they did. Now the problem with proteins is dust and aggregates. They scatter so much that just a single dust particle, which is, let's say, 10 times bigger than the protein, is going to scatter 100 times 10 to the 6th power, okay, actually 1 million times more than the protein molecule. So a single dust particle scatters as much as 1 million protein molecules. And you don't want to have this single dust particle inside there because then the data is going to be complete junk. So it's an experimentally challenging problem. But in terms of measurements, it's straightforward. You measure different concentrations, plot them, obtain the slope and the intercept, and you find the second virial coefficient and the molecular weight. The molecular weight serves as your feedback, how well you do measurements. The second virial coefficient is the valuable parameter that you're looking for, because you can know the interactions from that. Okay? Just clean this up. Just one more slide, a few questions, then a few experimental details. Now you can, I'm not going to go through this formula, time is running out and there are more interesting things to tell. You can take the full form factor without this one being equal to about 1. You can take this structure factor and then you construct the intensity with the form factor and the structure factor. When you rearrange that expression, you have this, which is a function of the molecular weight, the second virial coefficient, and the radius of gyration. When you vary theta and concentration, you can make a two-dimensional plot, which when extrapolated is going to give actually all parameters, all three parameters here in this expression. This is the so-called Zim plot. Again, you have the intercept here being equal to 1 over the molecular weight. This Zim plot would allow you, by just kind of, essentially you do measurements at concentration approaching 0 or theta approaching 0. So you do a set of measurements at different concentrations and different theta angles. In the previous experiment, the theta was constant, but ideally it would be small. In this experiment, you vary both theta and C, and concentration, in order to obtain three parameters: inverse molecular weight, second virial coefficients, radius of gyration.
How come we didn't use the intensity of PQ? Why did we use the field?
No, this one. If you remember, when I was deriving this one, this is actually this already squared.
Oh.
That's why you have this Q squared, R squared. So it's already the squared integral. I wrote this very, very kind of schematically, but I think you have enough formulas even without going through all the derivations. So when I gave you the original formula, it was for p to the power of 1 second. Now this p is not p to the power of 1 second. This is the real p, which is the squared one already. So this one is the intensity. And just kind of to follow up why this is squared and why we didn't have squared here. I mean, we have essentially this one is not squared because we need the square only once to calculate intensity. This one is a function which modifies the intensity. That's a function of the angle. Now, of course, if you have to do light scattering, whether simple or Z-plot light scattering, you're not supposed to plot these things on hand. I mean, every typical light scattering equipment these days is going to have inside build-up software, which is going to collect the data and give you the results. This, however, does not relieve you from the responsibility of taking precautions in order to get a good sample and so on, because if your sample is junky, your light scattering data is going to be junky too. And the software is not going to tell this likely. This is just a very basic slide which illustrates what we have been talking about. Why do you need neutrons, for example, or X-rays? Because if you compare let's say this is your typical protein molecule in real scale. Our wavelength of light will be about this big. The one of a neutron or X-ray is going to be about this big. Obviously, this one can resolve the structure of a protein molecule, but obviously from the viewpoint of a wavelength which is this large, for regular light, this is just a point scatterer. It cannot resolve any structural details. And finally, kind of something more refreshing here. If you go in the lab, what does your equipment look like? Laser. Your sample is typically in a circular cuvette right in the middle here of an optical bench, goniometer. You have, typically you're going to have a thermostating jacket around the sample so you know at what temperature you're working, because the NDC changes with temperature. So you have to be, it's the NDT, but I mean if you have N changing, I mean you're going to have problems, so it's thermostated. For the sake of the dynamic light scattering, which I'm going to describe at the time of my lecture, maybe next time, you need a correlator which also allows you to do, I mean you have a very fast processing board here in the computer. This is much spectrally kind of high-tech data collection done on a processor. You have a very fast digitizing board which allows you to measure the intensity in time. Typically equipment like that, these days you don't like equipment for static scattering only. You're going to buy equipment which both does static and dynamic scattering. The dynamic scattering is dependent on a very fast operating digitizer which allows to virtually takes nanosecond measurements of the light intensity. Photomultiplier which can rotate around the sample. So you can change what? Right, or Q. If you just have to have a structure factor or a form factor without many problems for a simple sample, you can make very easily a kind of homemade custom design devices. You just have a laser sample, a laser beam. You put in the sample, you put in a screen, and you register the diffraction pattern on a camera. And this one can give you surprisingly good results. Let me just demonstrate here. This is a structured latex sample which have a structure factor which is comparable to the wavelength of the laser pointer. So if you shine the laser through that sample, I guess you can see the ring, a single large ring. I want also to show this to the distance education students. So I'm going to
ask Chico.
Hey Chico, can you see that on the camera? The ring?
You have to move your hand.
Okay, so you can see like, I mean, you just take a laser pointer, you shine this through this monolayer of latex particles,
Move your hand a little bit. There you go.
and you can immediately see a very well-defined ring away around the central laser beam. You can see that this ring is extremely sharp. Now, what does this tell you about the structure of this sample? Right, it's actually ordered that if you have a small laser beam, now this is a large laser beam, so it integrates over. If you have a small beam, it's going to split into spots. Right now, however, because you have domains with different orientations, you don't see the spots, but you can see that eventually the distance between the two particles is exactly exactly the same. This distance, this is the characteristic distance which determines the radius of the ring. So if you just do this as a simple kind of custom-made device, you can measure the scattering angle and you can determine the structure factor in your sample. Okay, any questions so far? You can play with that with the sample afterwards if you like. Now, there is a very powerful method which you can use only in a few places in USA, but it's worth the scientific effort. And I've done this quite a few times. It's been a good experience. This is called neutron scattering. So I just want to let you know the basic here about neutron scattering. A very powerful technique. Now, in order to do neutron scattering, you need what?
Neutrons.
Neutrons. In order to have neutrons, I mean you have them all around, but you need special types of neutrons. So you also need a nuclear reactor. So what is not shown here is actually a nuclear reactor which will be someplace here in a confinement building. There is also what is called the source of cold neutrons. So the neutrons which come from the nuclear reactor are dangerous because they are fast. Now the wavelength of these neutrons is actually too small. What you do with these neutrons is actually you slow them down in liquid helium again somewhere else here. And from here on it's just like an enormous kind of like scaled up the equipment which I showed you here with the laser pointer. So of course the neutrons have to fly through vacuum, so you have this long vacuum line. You have the velocity selector which picks out the neutrons with a specific wavelength. It's just a rotating cylinder actually. They go on, keep on flying. You put in your sample here, and then you have this tube where you have this large detector. Now the size of this tube is about you can walk inside. So all this is you need like an enormous building the size of a factory actually, and you have lots of those. It's really an impressive site. I've been at the neutron scattering facility at NIST in Gettysburg. So you have like 8 or 10 of different types of scattering facilities and so on. You have the detector here can move forward and backward, which allows you to measure different Q values. If it's backward, you measure small Q's, small scattering angles. If it's forward, you measure large Q's. Now, in order to scatter, now you need scattering contrast. If you have particles in light, the scattering contrast is the difference in the refractive index. Now, what's the difference in the refractive index for neutrons? As it happens, the neutrons are best scattered by hydrogen. And again, luckily, they are not scattered at all by deuterium, which is, for those of you who have forgotten facts of physics, deuterium is also hydrogen, but it's just another isotope of hydrogen, heavier. Deuterium oxide is so-called heavy water. So typically your sample is always going to have hydrogen, so it's always going to scatter. If you put it in water, you're going to have so much scattering that you're not going to see anything. So typically your samples are contrasted, put in a media that does not scatter if you put it in heavy water. And one of the cutest properties of the neutron scattering is that actually, let's say this is your media, you have different scattering densities. By mixing heavy and light water, you can adjust the scattering density. Now imagine that these are micelles. Micelles have different amounts of hydrogen in the core and in the shell. if you put micelles in heavy water only, then you're going to have scattering from the core and scattering from the shell, which is going to be different. Imagine that you mix your heavy water with enough hydrogen, regular hydrogen, so the scattering from the heavy and light water is the same as the cores of the micelles. Then you're going to have scattering from the shells of the micelles only. The outer ring, the tails. Actually the heads. If you then adjust your media to be the same as the heads around the shell, you are going to have scattering from the cores only. So in one experiment you can actually do scattering from the micelles, you can do scattering only from the heads of the surfactant, or you can do scattering from the tails of the surfactant. So you get a very rich set of information about the structure of your sample by adjusting the contrast, the contrast of the scattering. It's an interesting experiment. It gives you lots of results and so on. Of course, you just don't work in such a facility. You have to write proposals and so on. But certainly this has been kind of a good experience for me and an interesting one. You can imagine what's the cost of this facility per hour. Kind of operating the cost of these facilities. I mean, it goes in thousands and so on. But of course, in this case, the US government is willing to support basic science, and that's good. You can use such facilities around. We're about out of time now. I had a few slides for dynamic light scattering. I'll probably spend a bit of time in one of the next lectures to finish off. This is important. I want to let you know about dynamic light scattering. But we don't have time to go through all those slides. So let's stop here and kind of take any questions, discussions, and so on. Yes, Daniel?
So, if we were to measure the structure factor with the improvised
Right.
Scattering
Uh-huh.
there,
Right.
then we could, from that, extract the size of the particles and...
Yeah, you're going to these are densely packed particles, so the structure factor is going to be exactly the diameter of the particles. Now these particles are immobilized, they don't move in water, so they don't have interactions. The structure factor is going to be the structure factor of the interactions are going to be equivalent of a total and complete attraction. Just because these particles have been crystallized into dense array, they touch each other in all possible places. So they cannot get any closer.
Is that what those are?
Yeah, this is a completely closely packed two-dimensional crystal. It's polycrystalline, so that's why you see a ring. You don't see spots of a crystal. But the point is that you can see that you have a very sharp ring, even in this kind of meager, pathetic light source. You can see this very sharp ring. This is just because the structure factor is so strong. I mean, the structure factor is essentially one sharp line, and that's why you have one sharp ring in the scattering. But it's very simple. And jokes aside, I mean, you can take a laser, a camera, and a screen. You can put in colloidal suspensions of droplets, for example, and you can do your own home kind of diffractometer and determine drop size distributions and lots of other things. People do that all the time. Okay, last question.
How is it related to the Bragg's diffraction wavelength?
The Bragg diffraction, now I have given you all the general formula for diffraction. Now this one, you can see that this is I have put in a radially kind of isotropic radio distribution function. However, if you substitute this radio distribution function with the function which comes from, essentially you take a structure factor like that, you're going to have also angular dependence, though. You have to integrate it over distance and angle. What you're going to have, you have discrete peaks in the structure factor here. And these peaks are also dependent on the angle. You are going to have discrete peaks in the diffraction pattern. So the Bragg formula is essentially the kind of, like obtained if you take this formula, and if you substitute here the distances between the particles in the crystal, you're actually going to get the Bragg diffraction formula.
But you could go the other way too, right? And find the distance between
Right.
these polystyrene.
Sure. I mean, like essentially, when you do the distance between polystyrene, you're going to take the Bragg diffraction formula, which is a subset of this formula.
Mm-hmm.
You understand? This is the general formula which gives you scattering from any structure in any configuration and so on. If you put in some structure where you know exactly what the distances between particles are and what is the angle, you are going to have essentially the integral is going to split up into a sum of peaks. So instead of a radial function of a ring, you are going to have essentially at some angles, which is going to the radial angle, you're going to have essentially a system of spots. So if you have a crystal, you are going to have scattering, let's say like that. This is the scattering from a hexagonal crystal. This is essentially the Fourier transform of the original crystal. The original crystal would be like that. This is the basic unit of the original crystal, particles together. If you scatter from such crystal, you're going to have 6 diffraction spots.
That corresponds to an HCP structure there?
It may. It depends on the, like, I mean, if it's two-dimensional structure, it will correspond to closely packed, hexagonally packed crystal. The fact that you have 6 particles in the basic unit of such a crystal, and you have 6 spots here, it's not that this spot is a reflection of this particle. You have 6 spots just because the symmetry is preserved in this type of mathematical function. So the Fourier transform is preserves the symmetry. If you have 6-fold symmetry here, you are going to have 6-fold symmetry in the diffraction spots. However, if you take the distance between, let's say, the center here and you calculate the angle theta, and if you calculate the distance here and the angle, you're going to say that you can immediately find the relation between these two is the Bragg formula, which you can obtain if you do the mathematics in this formula here. So the Bragg formula is just the kind of the simple version what happens with this formula when you know the distance and the angular orientation of the planes in the crystal and the scattering essentially planes.
Oh, was that one? That was the last question.
Okay, let's finish because our time is up. We're going to continue next time.